thesis on Faser, on the hardware commissioning and the software development of the trigger logic board. So I'll give a brief outline of my talk. It will run for about half an hour. First, I'll explain the context of physics at the LHC. Next, the new physics Faser hopes to discover, the location of the experiment, the detector layout and its components. And then I'll go into more detail into the hardware commissioning and the software commissioning of the trigger logic board. And so these last two parts are the part I worked on. And because as you might imagine, I didn't invent new physics, but I hope the part I worked on will help discover new physics. That would really maybe add a nice line to my LinkedIn account. So context. So Faser is a proposed experiment that will search for light and extremely weakly interacting particles. It has the prospect of discovering new particles such as the dark photon, dark Higgs boson, heavy neutral leptons, and Axion-like-particles. On the graph on the right, you can see that only 5% of the universe is known matter, and a lot is yet to be discovered. So Faser is important in that way. Faser is part of the CERN Physics Beyond Collider study group, which is a group aimed at exploiting the full scientific potential of CERN's accelerator complex and all its scientific infrastructure. So why not use the main detectors? Because at CERN we have ALICE, ATLAS, LHCb, and CMS. Well, these detectors, they focus on TeV scale particles with high transverse momentum, so high PT. So that's particles that travel perpendicular to the beamline. And Faser wants to search for a light particle with masses in the MeV to GeV range with low PT, so particles that travel parallel to the beamline. These extremely weakly coupled new particles will travel hundreds of meters and will not interact with any material before decaying to known standard model particles. So Faser will not be placed in the beamline, but 100 meters along the line of sight. These new particles will not be bent by magnets, but they will travel in a straight line, and then their decay products can be spotted by Faser. So what are these long-lived particles? So they're light and weakly interacting. It means that they're long-lived, so it takes time to decay, and they could be the bridge between normal matter and dark matter. And these might be produced in the decays of mesons, so decays of pions or kaons. Here we see the ATLAS interaction point and the proton-proton collision that produces a lot of particles. And we see this A prime, which would be a new particle, maybe a dark photon. These new particles would be very collimated with the beam, so the angle would be small. If we do this simple calculation so that the angle is roughly the mass of the pion over the energy, with the mass of the pion 130 MeV over 1 TeV energy, then it means that if we place the Faser at 500 meters, the spread would be of 7 centimeters for pions and 25 centimeters for kaon. So that means you can have a very small and compact detector, and that's inexpensive as well. The TI-12 tunnel, so Faser will be placed in this TI-12 tunnel along the line of sight, and it's a disused tunnel, so it's perfect to place the experiment. So these LLPs, so light and weakly interacting particle, would travel through the ground, through concrete, without interacting, and then will decay into Faser. So here we see these blocks are the beamline, the proton-proton beamline that's curved by the magnets, but these LLPs will travel in a straight line. So a schedule. So now the CERN is in a long shutdown too, until the end of 2020. And this is the perfect time to build, install, and test Faser before the magnets cool down. And then Faser can take data during the run 3. Here you see that in 2024, there's another shutdown. And this would be a nice time if you want to install a Faser 2, so a bigger and larger Faser. So Faser 1 would be maybe a proof of concept, and if it works well, then you could build a Faser 2. So what kind of new particles does the team hope to discover? It hopes to discover maybe dark photons. They're a hypothetical hidden sector particle where the interaction between the hidden sector and standard model are weak, so that's why it was hard to discover. It's indirect and would be mediated via gravity or new particles. It's the dark photon is proposed as the force carrier, so it's like the photon in the SM, but with a new abelian U1 gauge symmetry. And this new spin-1 gauge boson could couple very weakly to the electrically charged particles through kinetic mixing with the normal photon. So this would be the decay mode of the neutral pion. It would decay into a gamma and a photon and a dark photon. And here we see the branching ratio of the neutral pion that goes to a dark photon is roughly the same as the neutral pion goes to gamma gamma, but it's modified by the mass square of the dark photon. So how would we produce these dark photons? It would start at the Atlas interaction point, and we would place Faser, so 480 meters along the line of sight. And here neutral pions would be produced in the proton-proton collision, and they would decay into dark photons and photons. These dark photons would travel and decay into the decay volume of Faser, and then this dark photon would decay into positrons and electrons that would be separated by magnets, so you could see the tracks of these standard model particles. What's the signal signature of this dark photon to positron electron? It would be no signal in the veto scintillators, and then the A prime would decay in the decay volume and produce two tracks from the positron and electron. And then you would observe a large blob of energy in the calorimeter. So these decays, again, would be very collimated and of the order of the milliradian. So that implies that after 1 meter, the separation would be of only 100 micrometers. This is why you need strong magnets to separate the tracks so that you can really reconstruct the momentum. Another example of new physics are Axion-like-particles. So they're new particles supposed stable, neutral, and of a very, very low mass of 1 millielectronvolt to microelectronvolt. And they were already invented in 1978 by Wilczek and Weinberg. So it's a null theory, but I hope we can discover them. And there's a possibility of using the LHC as a beam dump experiment, where you take these very high energy photons produced in the IP that could hit the neutral beam absorbers, or TAN, and these would produce ALPS, these Axion-like particles, via Primakov effect. So the TAN, so these are the two beamlines, and the TAN is located here. It's material designed to protect the magnets. So these photons would hit the material of the TAN and then produce via Primakov effect either a neutral pion or a Axion-like particle. And if it produces a neutral pion, then this one would then decay into gamma and Axion-like particle. So again, the production of the Axion-like particle would be, it would start again at the Atlas IP. You'd have a neutral pion that decays into gamma gamma. And this gamma would hit the TAN, produce an Axion-like particle via Primakov effect. And the Axion-like particle would travel to Faser, decay in Faser, and decay into two photons. However, these two photons, the tracks would not be separated because it's a neutral particle. Even if Faser does not find new particles, it could still be useful to probe the standard model to more details. It could help us understand forward and cosmic ray physics. It could also give us a new insight into neutrinos. So for example, in run 3, 10 to the 13 muon neutrinos with energy of 100 GeV will pass through Faser, and roughly 600 of them will interact in this 10 centimeters thick block of lead in front of Faser. And also a few tau neutrinos will travel to Faser and interact with it, which is a rare particle to see. So what's the location? Where would you put the Faser? So it will be at Geneva in the LHC. And here we see an old map. So this is the electron-positron accumulator, the proton synchrotron, and it goes to the SPS. And here we see it used to be an old injector that went into the LEP, but it's now disused. But this would be the perfect spot to put Faser. So Faser would be situated, so this is the interaction point of Atlas, where you have these proton-proton collision. And Faser would be situated 480 meters along the line of sight, just below this curved ring, which is the 27 kilometer ring. And here we see on the left, so these again are the two beam lines, but pay attention to the y-axis, which is in centimeters, and the x-axis, which is in meters. We see that the charged particles are deflected by the magnets and then go into the beam. The neutral particles are absorbed by the TAN or the TAS, and only ALPS will travel through matter, through concrete and rock, and then decay into Faser. And expected in the standard model, only muons and neutrinos will arrive in Faser. It will be situated around 5 meters to the side of the beamline, so not very far apart. We'll need a little civil engineering work to dig the tunnel and put the Faser in the line of sight of the IP. So we see here the trench. And the maximum digging depth will be of 50 centimeters. This is the maximum allowed to avoid the drainage membrane where the water runs in case of, I don't know, a flood or a rainy day. There's a detailed study by a CERN Civil Engineering Department that has been made. And with this design, you can fit a 5 meter long detector centered on the line of sight. So the trench has been dug in the last few weeks. So it's very nice. And on the right, you can see this yellow protection material designed to protect the beam when you transport instruments from the elevator that goes to the ground to the TI-12 tunnel. So it slides if you drop it. So the detector layout and components. So the beamline will come through the left and hit first these two scintillators. This is a scintillator and lead veto station, where these two first scintillator will veto high energy muons. Then this black square is a photon shield that converts photon into, oh sorry, it's a lead photon shield that converts photon into electromagnetic showers that can be vetoed by the second pair of scintillators. Then there's a decay volume with a magnet around it where these dark photon will decay. And next is the most important part, it's the spectrometer. It's composed of two 1 meter long magnets with 3 tracking stations to see the tracks, as well as scintillators at the beginning and at the end. This is to do triggering and timing. At the end, there's also an electromagnetic calorimeter to see the EM energy. So the magnet will be a 0.6 Tesla permanent magnet. So permanent is very nice because this minimizes the need for power and cooling. And it uses a Halbach array design. This means that you have a high magnetic field in the core, but almost none outside. It will be the most expensive piece of equipment needed for a Faser. It will cost $500,000 francs. So the tracking stations, there's, as I said, there are 3 tracking stations, and each of them is composed of 3 layers. So each of these stations has 3 layers like this, and each of these light blue squares are actually SCT modules used to see the tracks, for a total of 72 SCT modules. And these were actually used in Atlas and are spare parts. So this keeps the cost of the experiment down. So it's a small budget of, it's under 2 million francs, but this is the grant from the Heising-Simons and the Simons Foundation. And I say it's a small budget in comparison of the total budget of LHC, which is 13 billion francs. So I mean, it's high reward, low risk, high reward. If you find new particle with a small experiment, then it would be very nice. So now we go to my part, the hardware commissioning of the TLB. So this is the DAQ architecture. So you have in gray all the sub-detectors, so the tracker modules, the scintillator modules, the calorimeter, and they all go through electronics to decode the data, and then it can be sent on the surface to certain storage for analysis. But you need electronics to take the signal from the detectors. You need in particular a TLB, a trigger logic board, that takes care of these two detectors, and a tracker readout board. So they both use the same Unigeo USB 3 GPIO board as a core module, which then you can add an adapter and a mezzanine to either become the TLB or the TRB. This is the TLB, and you can see the 8 inputs are actually these 8 trigger lines. So I had to focus on this for the TLB. What's the role of the TLB? So it's designed to send L1As, level 1 accept. It means, so the scintillator have a lot of signal coming in, but maybe you only want to select a few of these events. Otherwise, you would fill your hard drive. And this is what it does. It's a selection of events, the L1A. This is the TLB schema. So it looks complicated, but basically it takes these 8 signals, does a bunch of coincidence logic, and then outputs an L1A. So this I'll go through in the next slides. How do you control the TLB? Well, you have a nice GUI that has 3 tabs, and this tab is used to start and stop the DAQ, so the data acquisition. It's also used for slow control, so to send maybe software triggers. The second tab is used to toggle trigger lines. So this is basically the initial configuration of the board. Maybe you can change the prescales you want to apply. And the last tab is the LUT, the Look-Up Table. This is to do the coincidence logic. So this GUI was used for initial testing and will be later replaced by a common framework software, because as you can imagine, it would be hard to have different GUIs for every subsystem. It would be nicer to have a big GUI with to control every subdetectors. This TLB can output trigger and or monitoring data. Monitoring data just takes the last maybe 100 events, 1,000 events, and then does statistics on them. So what is a lookup table, a LUT? So it takes these 8 bits, these 8 trigger lines, and converts them into 4 trigger lines. So 256 inputs go to 16 inputs. So how do you configure? You have these 256 inputs, and then you have to, the user has to select the value he wants to assign to each of these inputs. So here, as an example, I said, oh, I want, when I have the first signal to 1, then give me back a 1. So this is how it would be represented. Let's say the first scintillator has a signal, then it converts it to 1. So this is an easy example. If you have maybe the second scintillator, then maybe this is very important. So you want all 4 trigger lines to fire. And if you have a coincidence between 2 scintillators, then you would say, code me the third trigger line. And you have to put a 4 because this is in bits. So this is the coincidence logic, which requires very low computing power because everything is already pre-decided. So first thing I had to do was to test all this chain of commands to understand the TLB board. And I had this nice assembly at the CERN. It was in the scintillator lab where you have this pulse generator that sends pulses to the oscilloscope to see the signals. It goes back into the digitizer and into the TLB, and everything was controlled via a remote PC. So first thing was the sampling phase. So as you saw before, the signal go first into a digitizer that converts the analog signal to digital, but it outputs only at 125 megahertz. So that means the signal have an 8 nanosecond jitter. A jitter is when you see this pulse, it can oscillate. It's not precise on a fixed clock cycle. It can oscillate between -4 and +4 nanoseconds. So this is an issue when you want to have precise timing between a proton collision at the IP and its arrival in Faser. You want it to always have a fixed number of clock cycles between the IP and Faser. However, if you trigger on falling edge of the clock of your clock, then you would have maybe sometimes it's trigger on this clock, or maybe it's sometimes it's trigger on the next clock. Whereas if you sample on the rising edge, then you'd only have this one clock. So this would be perfect for us. However, because you have a lot of scintillators with different lengths of cable, then you need to change this sampling phase on the falling edge or rising edge, depending on the length of the cable. And this would only be done at the end when you build the experiment. So to test this, I first need to quickly explain what the BCR is. So as you know, the proton travel in a ring, and they're all bunched in a kind of chain, where so they're in bunches, it's called, where the locomotive has a bunch of protons, and every car is a bunch of protons. And whenever one bunch does a full loop, well, the first bunch does the whole loop, then you have a BCR signal. So a BCR is just a clock that sends a signal every 11,000 hertz. So for the testing of the sampling phase, I had this the TLB that has this BCR signal as an output that I plugged into the digitizer. Here we see on the right, in green is the TLB, and red is the digitizer. So it receives this BCR signal, digitizes it, and sends it back to the TLB. And then I can take a look at the level 1 accept of the TLB. And here we see the results. So we had, as expected, 2 clock cycles if I sample on the falling edge, and 1 clock cycle if I sample on the rising edge. And this was done, so you can select which edge you want to sample on with this GUI, with this bit on the GUI. So this worked very nice. Next is the input delay. So as I said, the phaser is 5 meters long, and to do some coincidence on signal, the first and last detector will be out of sync. So maybe they'll be at 65 clock cycle, and the last one will be 67. So you would need to delay the first one by 2 clock cycles and the middle one by 1 clock cycle to have a coincidence. For testing this, I took the same BCR signal, but this time I split the 2 cables, this cable into 2, and one was at the beginning of the phaser, and the second one had a 30 nanosecond delay to mimic, the length of phaser. And then I checked the L1As. And so here we see on the scope, the 2 signals were far apart, so I couldn't do coincidence. However, if I delayed by 1 or 2 clock cycle the red one, the first one, then I could do a coincidence and produce an L1A. Next is the prescales. So maybe you want to sample the incoming data and only want a fraction of it. So this is what a prescale is. If you set it to 1, every signal you send to the TLB, you get an L1A. However, if you set the prescale to 2, only 1 in 2 signal you send to the TLB gets an L1A. So here we see in yellow are the signal I sent to the TLB, and in pink are the L1As. And prescale set to 3, 1 in 3 signal get pass. Prescales. Next is the random trigger test generator. So there's a nice option. Maybe you don't have subdetectors to produce signals, but you can produce random triggers at a random time. But there's a user settable average pulse rate, so you can set the average rate. So this follows a Poisson process, with an exponential. And when I tested, so the random trigger has 8 settings that ranges from 0 to 7. And when I tested these, it follows as expected an exponential, with the average time between the random trigger increasing with the setting. So that's the random generator. Then the sources of dead time. So every time you have an L1A, that the TLB sends an L1A to the subdetectors, that means the information is important, and all subdetectors need to read their buffer and save their memory or information of the signal. So maybe you want to say, after you have an L1A, please don't send me another L1A because I'm busy saving this data. This is the simple dead time, where you say there's a number of clock cycles after an L1A where a new L1A is vetoed. Next is the BCR dead time. So every time you have a BCR, then the tracker needs the time to send a BCR command. So this means that a few clock cycles before and after the BCR, you cannot have an L1A. Then there's the busy tracker dead time. So whenever the tracker receives an L1A, they need more time to save the data. And so they'll communicate to the TLB, calm down, just don't give me L1As at this moment. And then there's the rate limiter. So this is to avoid noise, so too many signals. And this keeps the rate under 2.25 kilohertz. And it limits the 3 L1As in 15 turns. So this is how I tested the rate limiter. So I sent a BCR signal in the TLB. And as you can see, there's only 1 in 5 signal that go through. So this is because of the rate limiter. Rate limiter. Next, the simple dead time. So here I send 10 pulses, quick pulses. And as you can see, the first signal gets an L1A, the second one as well. And there's only 3 signals instead of 10 because of the rate limiter. And if you change the dead time setting in the GUI, then you can space out L1As between them. So here with the dead time set to 10, it's 10 clock cycles of 25 nanoseconds, so 250 nanosecond delay. Next is the BCR veto. So this is a histogram of BCIDs that ranges from 0 to 3,563. And this is just the bunch crossing ID. And so this is a zoom on the beginning and on the end. And you see there's a gap here and here of 9 BCIDs. And this is exactly what we needed to for the tracker to send their BCR command. And so that was it. So I couldn't test the tracker controls because you need to plug in the tracker in the TLB, and these were not very ready to communicate yet. But otherwise, everything worked fine. Next is the software commissioning. So so as I said, this is needed to replace this standalone GUI and integrate the TLB into this Faser run control. So the Faser run control is a big GUI that controls all subdetector into one place. As you can see here, you can see all the status and setting of the subdetectors. You can change the configuration, see if it's maybe has an error. Here's the control panel where you say start the experiment, stop the experiment. Here there's the configuration files. And here you can see live graphs of physics event. And each subdetector is called a module. So maybe you want to add new scintillators, then you can simply add a module into this big GUI. So to write this software, it's nice because both the TLB and TRB use the same GPIO board and the same low-level software control. So this low-level software was already written, and I had to write the TLB access, so the software to access and read out the TLB. and the tracker access was already written, so I could get inspiration from it. The base function is send and retrieve. So it has three variables. So send and retrieve is to send information to the TLB and then read back the TLB. The first one is the command ID, which is the address in memory where you want to send your command. Then is the command argument, which is the payload you want to send, the bits you want to change. And then the answer argument where the board tells you back, oh, it succeeded or there was an error in the transfer. So what does the TLB access software is supposed to do? It's an API to communicate with the TLB, and basically takes this JSON config file. So maybe you recognize the sampling phase, the input delay. It parses this JSON config file, stores it, and then uses it as a variable to configure the TLB as described by this JSON. So the config file can be changed via a text file or via the run control, which has a nice drop-down menu where you can select sampling phase on or off. So how do you access memory? Because during the bachelor at Unigeo, you don't have electronic lessons and very low software lessons. So it was new to me. But basically, if you want to change the input, the sampling phase, then you need to find the right bit, which is like a switch, and then switch all the bits you want to change. And the configuration is split into 15 words of 16 bits, where the four most significant bit code for the word number, and then the rest in gray is the payload. So here the sampling phase, these are all the switches, so you can turn them on or off, and this will change the sampling phase. Some information can be split into 2 words. So for example, this prescale is on word 2 and on word 3. And it's you need all the 8 bits, read 8 bits to code the prescale. So this is nice to optimize memory space, but it's a challenge because you need to send 2 send and retrieves just to change 1 information. So this is a function I wrote to configure and verify the TLB. It takes as an input the JSON config file, and then it runs a big loop that says, did you configure the board successfully? If not, then run this big function that first cleans the board. It wipes all the bit and makes a clean slate. Then it sends the config and the direct parameters. It then checks if the board was configured correctly. And if not, it tries again, maybe X number of time. Otherwise, it goes to the next step. So then this is the TriggerReceiver Module. As I said before, it's the module that goes into the run control. And the configure TLB was just the function we saw on the last slide. And whenever the Faser run control wants to start the experiment, then we'll press configure. And every module will receive a configure its module command. So for example, for the trigger logic board, it will configure TLB, configure the LUT, and when you press start, it will start the readout and create 2 loops. The first one is poll data that keeps listening to the TLB and says, oh, I get this signal, and it will store it into mTLB event data in a loop. And on the left, there's another loop that takes this mTLB event data, decodes the data, and keeps decoding the data until you press stop. So here you see all the subdetectors, so all the trackers and TLB, as well as the digitizer. They all have this kind of loop where they decode data, but they're all running in parallel. However, maybe you want to save one physics event into one event. So that's why you need to decode the data and maybe wrap around a header file that says the date and what the run number is, and then stitch all these information together to form one physics event that can then be sent to permanent storage in a hard drive. So that's it. So no new physics in high PT region of proton-proton collision has led the search for light and weakly coupled LPs. Faser is a small and inexpensive detector installed in the far forward region of proton-proton collision. It will correct data during run 3 and probe new regions of the parameter space for new particles with masses in the 10 MeV to GeV range. It has a small 5-meter long footprint consisting of magnets, tracker planes, scintillators, and a small calorimeter. It has a TDAQ system for trigger and readout with the TLB as the main component. The hardware commissioning and software development of the TLB has been completed and is now ready to be used for commissioning of Faser. Cosmic data is being taken with the TLB using scintillators and calorimeter, and soon with trackers as well. The TLB is an essential component for Faser's operation during run 3, and it can be integrated in the bigger and more advanced Faser 2 in 2024. So thank you very much. And if you have questions.